Hey, welcome back to Unit 9, the gas laws. This is the second recording in the series, and we will be talking about in this recording the variables that affect ideal gases. And so we'll hold off on the math just a little bit, but in this recording we'll set the stage for understanding why the relationships happen the way that they do. How come the pressure affects the temperature, and the temperature also affects the volume of the gases. And so let's get started here. And the first thing that we're going to talk about is just the variables in general, and in light of these ideal gas law properties. Ideal gases are ones that are not under extreme temperature and pressure, and so they don't have intermolecular forces acting upon the particles. They don't stick together. They don't condense. They are moving freely and colliding freely, and the collisions are said to be elastic, which means that they don't lose any energy. And because of these variables, because of these factors, the variables of pressure, temperature, and volume, and the molar amounts of the gases can be easily predicted by these empirical gas laws. Okay, and the first variable, pressure. Pressure is equal to the force exerted by a gas divided by the area it is applied to. So you can think of it like a lady's high heel. If you were to be under a lady's high heel when she presses down, that force would be felt a lot, because it is a very small area and you're applying a lot of pressure to that area. So the scientific unit of pressure is the Pascal, and the units for the Pascal are kilograms of force divided by the meters times the second squared, where some meters in the second square part of it are the area that force is applied to. In chemistry, we tend, instead of the Pascal, let's use somewhat in some areas, but in the United States and in science in general, I think that the atmosphere and the torr are used more frequently. Another way of expressing torr is millimeters of mercury, and we'll see why that is here in a second. Just the different terms to mean the same thing. Okay, so continuing on with our discussion of pressure. Pressure is measured, barometric pressure, or the pressure that's all around us every day, is measured in a device called a barometer. And there are different devices used now, but we will talk about the mercury barometer as our illustration of how atmospheric pressure is measured, and talk about this measurement of torr and millimeters of mercury. Okay, so the barometer, I have an example here of a barometer, and the barometer is a inverted tube. And so what they do is they take a tube of liquid and they invert it in, turn it upside down. This is a closed end, and they invert it into a vat of the material that's in the tube. And traditionally it was a mercury barometer, and so you can see here that this meniscus is kind of funny. It's going the other way, and that's because the mercury holds on to the side of the container tighter than it does to the molecules in the mercury, and so you have a meniscus that kind of goes opposite of a water meniscus, or a curve here, and it's inverted into a vat of mercury. And so what happens is, when the atmospheric pressure rises, it presses down on the surface that's in the container, and the mercury rises. So high pressure means a higher column of mercury. At about 1 atmospheric pressure, this level is 760 millimeters of mercury. So normally, under normal conditions, It may be a little less or it may be a little bit more depending upon that atmospheric pressure at the time, but it's always close to 760 millimeters of mercury. So it says here, as the atmospheric pressure changes, the level of the liquid in the tube rises. A barometer is a device used to measure atmospheric pressure. And a tube that contains a liquid is inverted. Okay, we already talked about that, usually mercury. And so you might jot down here that under normal conditions that this mercury reads to be about 760 millimeters of mercury. And we call that 1 atmosphere. And instead of having millimeters of mercury, sometimes they just say atmospheres, 1.5 atmospheres or 2 atmospheres, or maybe it's not quite 1, maybe it's 0.98 atmospheres if we're experiencing low pressure. So at the atmospheric pressure that changes, the level of the liquid in the tube rises. And you can write all this down to help you remember how this works and pause the video accordingly. The atmospheric pressure exerted causes the height of the column in a standard mercury barometer to be around 760 millimeters of mercury. And we say, we also call that a torr, okay, or we use the indications, we don't call it a torr, but we call that measurement torrs. So instead of 760 millimeters of mercury, you'd say 760 torrs. Means exactly the same thing. The name was given in honor of Evangelista Torricelli. If I butchered his name, I apologize, who invented the mercury barometer back in 1643. 1 atmosphere is equal to 760 torrs. We'll be using that a little bit later on in the ideal gas laws to make some conversions. So it's helpful to have that as a reference. Temperature is a measurement of average kinetic energy of particles. Okay. Sometimes this gets confused with heat, or temperature and heat get used interchangeably, and that's somewhat okay, but we have to make some important distinctions between heat and temperature here. Heat is a transfer of energy from one object to another. And an increase in heat does not always result in an increase in temperature because of phase changes. Alright, and so here I have a nice container of boiling water. And if we had a thermometer inserted into the boiling water, we would find that the temperature of the boiling water would top out at around 100 degrees C. This is important to note here, is that it's not always 100 degrees C. It depends upon the atmospheric pressure. But at 1 atmospheric pressure, or 760 millimeters of mercury, the water will have a temperature of 100 degrees C. And you can keep applying heat to this water in that temperature will not go above 100 degrees. Because as the water molecules are moving, they can only travel so fast before they escape into the gaseous state. If you held your hand over here, you would have some nice water vapor. Sometimes they call it steam, and it can burn you rather quickly. So you have to be careful with that. So that's what I mean here. There's a difference between heat and temperature. Heat is a transfer of energy. Temperature is a measurement of particle movement. And just because you heat something up does not mean the particles, well, it will mean that they move faster, but you cannot always measure how fast that they are because they escape to the gaseous state. Temperature scales. Okay. So Celsius is the most used measurement in science. The freezing point of water under standard conditions is 0 degrees C, and the boiling point of water is 100 degrees C. The Kelvin scale is used for gas measurement because it's an absolute temperature scale. It is a scale with no negative measurements. And this temperature scale makes it really nice when you're making predictions about gases, because you can predict how an increase in temperature will affect the volume, or a decrease in pressure will affect the temperature, for example. So the Kelvin scale is used because it helps make the variables within a gas very predictable given that they're in an ideal state. The freezing point of water on the Kelvin scale is 273 degrees. Okay, so the boiling point is 373 degrees. And so what you'll notice here is that there's exactly the same number of units between the freezing and boiling point on the Kelvin scale and the Celsius scale. So those units are equivalent, but the numbers are different. And it makes it really easy to go back and forth between the two scales, because you can just add or subtract 273 to get there. So I have a helpful, it's important to note the increments are both the same. We just talked about that on both scales. And here we have some conversions. All right, so you'll notice here that that's not true of the Fahrenheit scale, which you may be more familiar with, because we use the Fahrenheit scale to denote temperatures, atmospheric temperatures. So we're more familiar with this Fahrenheit scale, but in a chemistry lab or any kind of lab, science lab, you'll usually measure in degrees C, and then if you have to do some gas law problems, you'll convert that to Kelvin. All right, so I think this concludes recording 2, and in the next recording we'll talk about specific ideal gas laws, Boyle's law, Charles's law, Gay-Lussac's, etc., and do some more math. So looking forward to seeing you in the next recording.